we don't have to constrain ourselves to just one input variable, one input node. We can have multidimensional inputs. So all we need is the data to support that. The perceptron, the architecture, handles that really easily. We just need a spreadsheet that has a column that we'll call x1 and a column that we'll call x2. And we just need a whole bunch of data. You know, these have some values. I don't know what they are. I'll make up some numbers. 6 and 20, 8 and 15, and so forth. Who knows? So these are our inputs. And we'll usually have some data on the thing we're trying to predict. And again, this is going to be binary. So this is our outcome, our output variable. Zeros and ones. We saw something just like this when we did our logical functions. We had, you know, is the person a catch, yes or no? And it depended on whether they were, I forget now, I think it was like smart, yes or no, and funny, yes or no. But then when we used Desmos, or when we did our perceptron update rule worksheet, we weren't constrained to just zeros and ones on the x's. We had continuous variables. The idea is just like before, we're going to take our x's, we could take this first set here, and put them into our input layer. So this is going to become a 5, this is going to become a 13, and then we take these values, multiply them by their weights, potentially add a bias, and then we just do the familiar. We multiply our values times our weights, add a bias, and then we add we push that through to a nonlinearity. What's often called an activation function. The idea is that if you load up a neuron with enough juice, enough electrons, then the neuron will fire. It will release an electrical discharge. So it'll be activated. And we've seen that the standard perceptron activation function is if C is bigger than 0. In other words, if it's positive, predict a 1, otherwise predict a 0. So it's the same thing. We really didn't have to do anything different to support multi-dimensional inputs. We just need to have another column of data and feed that into the model. Take each observation, multiply it by its weight, aggregate everything, and then see if it's positive or negative. And then we could do that for every single row in our data set. We take the second one, we do it again. Multiply, now we do 6 times that weight and 20 times its weight. Tack on the same bias and then apply this same rule. And then we're going to do 8 times W1 and 15 times W2. Tack on the bias and again see if we get a positive or a negative number, and that'll tell us whether we get a 1, a 0, or whatever for our output. So it's extremely easy for a perceptron to incorporate multi-dimensional inputs. Now, we've actually seen how this works like in a graphical format. The graph is a little bit more complicated because here I really have 3 dimensions for my data. I've got x1, x2, and y. And it's hard to draw something on a screen in 3 dimensions. So, so what I'm going to do is kind of fudge, and I'm going to have x1 and x2 on the plane, and then you can imagine my y variable kind of like floating above them. But I don't like imagining. So what I'll just do is we could color code the y values, or we could just label them 1s and 0s. And so let's just say we had our data here, a bunch of 1s and a bunch of 0s. In our task for the binary classifier that we have, it's a binary, so we're trying to classify something as a 0 or a 1. is to come up with a line that splits our data. Just like that. In this one here, we split it perfectly. Now, we're going to see in a moment that this is actually just like regression, even though it looks a little different. And I'll define regression in just a moment. I just want to point out before I do that there was nothing special about going from one-dimensional inputs to two-dimensional inputs. You just need to add on an additional term into this z and then see if the result is positive or negative. So we could just as easily have three inputs, a three-dimensional input and one output. Now I mentioned regression, and now it's time to talk about that. Regression is what we call any time when the y that we're trying to predict is continuous. So before we had y was a binary, and we called that classification. Now if y is continuous, we call that regression. So the nature of the output determines on whether this process, thing that we're trying to do, is called regression or classification. And what we'll see is it requires almost no change at all to the perceptron model to switch between these two. It's the most trivial change you could imagine. In fact, regression is in some sense a whole lot easier. But what is regression? Hopefully you've seen instances where you've got a scatter of points, xy points, something like that, and you're trying to fit some line to it, some line that fits best, and that's called the regression line. Okay, so maybe we have the weight of a car, and we've got the price of the car, and I want to come up with some line that'll help me predict the price. Again, I apologize. I'm using weight here in two different ways. It's my x variable, but it's also the slope here. It's the parameter that I'm multiplying x by. Now, students usually, oh, by the way, I've done this with that actual data set, this 1978 cars data set, and that's what we see. Right, so heavier cars, they were bigger, and people didn't care about gas efficiency back in 1978. So bigger was always better, and the car sold for more. Kind of like how an Escalade, any old Cadillac, is a big car and it sells for a lot. That was the idea. Now, students kind of look at this and they go, that these look like opposite problems, classification and regression. That's especially obvious when you compare, this picture and this picture here up on the top right. See, in this top right picture, it doesn't look like I'm trying to fit the points. It looks like I'm trying to separate them. Whereas here, it looks like I'm trying to fit them. Actually, it turns out we're doing the same thing. Literally is a matter of perspective on how they're different. Literally have to just change the angle that you're viewing this data at. This picture here has two inputs and one output. That picture has only one-dimensional input and one output. I think that might be part of the problem. It is hard to draw in 3 dimensions. Let me pull up Desmos and try to point out how regression and classification turns out as the same thing. So I'll be right back. Okay, so here's a three-dimensional problem, but we're projecting it onto a two-dimensional plane. My vertical axis is x1, my horizontal axis is x2, and the value of y, the thing we're trying to predict, is a 0 or a 1, depending on whether it's green or red. And so this is a classification problem. We've seen stuff like this before. We know that we're trying to separate our greens from our reds. So I've got here a perceptron that's been trained already. And you can see it now in white, kind of, where above the white line, it's predicted to be green. Below the white line, it's predicted to be red. It's predicted to be 0. Above 1, below 0. So we're comfortable thinking of this as a classifier. But gosh, doesn't it look like that line isn't trying to go through the points? Which is very different from this, where the line is, it's definitely trying to go through those points. Here it looks like, here the line is not trying to fit the points. I'm not trying to like get the line of best fit. Here it looks like it's trying to split them up, almost like it's the opposite. Here's how it's a problem of perspective. Let's literally now just change the angle that we're viewing this on. All right. What we have here is actually a step function. Right? Below this, 0, and then 1s. In fact, if you want, this is exactly our z function this way. Where it's to the left, it's a 0. Where it's to the right, it's a 1. But notice that the function that I'm doing, like, it's best described by this gap between these, but it's an S function. It's hard to draw that. The function that we're fitting actually does fit the scatter of points as best as possible. In fact, it makes no errors whatsoever. It fits perfectly. That red plane is going through all the red points, and that blue plane is going exactly through all of those green points, exactly as it was supposed to. So this line that we fit, it's actually an S. That function that we fit fits the data best. The problem is just that it's S-shaped function. But the goal is still the same. We're trying to fit the data as well as possible. Here, or here, we're still trying to fit the data as well as possible. It's just that this function doesn't fit the scatter of points nearly as well. The idea, though, the critical idea, is you're trying to fit a function to a set of points. When those points are continuous, we call it regression. When those points are binary, we call it a binary classification. So how do we get a perceptron to give us regression, to give us this rather than this stuff? It turns out it's really easy. Hang on a second. Let me clear my screen, and I'll be right back. Okay, so we have a familiar perceptron type model. We have data on x's. They can be whatever. They can be binary. They can be continuous. x1, x2. And now we have data on y. And for this regression problem, the y is a continuous variable. So we're trying to predict the price of the car or something like that. So maybe one car is 30,000, another car is 50,000, another one is 110,000, nice car, and so forth. And maybe we've got, maybe we have whether it's domestic or foreign, that could be binary, and then we could have, the kilograms of the car, some other continuous variable. Doesn't matter. Maybe it's 5,000 kilogram car. All right. Take each data point and feed it into, take your inputs and feed them into x1. So feed in 5k, feed in a 1, multiply these by their weights, tack on a bias, and then hopefully we'll get 30,000. Okay. So we have 5,000 times W1 plus 1 times W2 plus B. And here's the thing. We're not going to do our usual next step. We're not going to squeeze this straight line to be 0, 1. We're not going to do the nonlinearity. In fact, we're just going to stop with the linear. And that's our output. That's why what we're getting was a straight line that fits this scatter of points as well as possible. So it turns out regression is actually easier than classification, which is awesome, right? How often is that when things get easier? Not too often. All right, now there's still one thing that we haven't been able to figure out how to do. We still haven't tackled the XOR problem. And, we would like to be able to do far more complicated curve fitting or more complicated classification, something like XOR. We would like to be able to have curves that fit the data as well as possible. So there's two real ways, meaningful ways, to add complexity to our perceptron model. Up until now, they've basically all been trivial. The change has basically either been in the data or not adding this nonlinearity. So what is this more meaningful changes that we're going to do?